closed or thinking here, I guess, where you shouldn't think always of dynamically evolving stuff, but sometimes theoretical physics or usually the idea of thinking about elements of reality is really physics. But today I was talking about information-theoretic reconstructions, something a lot of people here have done as well. And I'm really looking forward to this talk.
Thank you, Marcus. All right, so this is my pointer. Thank you very much for having me. Usually when I give a talk, I know more about the subject than the people in the audience, but today it's the reverse. I'm not in quantum information theory, and yet I'm going to be talking about what you guys have discovered in these reconstructions, trying to make sense of it from someone who's not in quantum information theory. I'm in foundations, but I'm not in quantum information theory. And this is only something I've discovered recently with my co-authors on these papers, that you guys have had this figured out for some time, and we're just catching up now. And I'm hoping to be able to run this by you and have you correct what that needs to be corrected about, and then I can take this to the foundations community and try to sell it there, because I think you guys have, I think your reconstructions have made sense of quantum mechanics. I think you're good to go. Okay, so here's this is the picture. All right, so making sense of quantum mechanics. And I'm going to present it as if I'm presenting, to a generic audience. So this is, don't be insulted. I'm sorry. All right, so Feynman won a Nobel Prize for his work in quantum theory, and yet he famously said, "I think I can safely say that nobody understands quantum mechanics." Gell-Mann won a Nobel Prize for his work in quantum theory, and yet he said, all of modern physics, governed by that magnificent, thoroughly confusing discipline called quantum mechanics. It survived all tests, we all know how to use it, and so we've learned to live with the fact that nobody can understand it. So clearly they must understand something about quantum mechanics if they got a Nobel Prize in it, right? So what they're talking about, obviously, is the fact that quantum mechanics, as it stands now, is a mathematical formalism. It maps beautifully to experiments, and we know how to use that. The question is, why does that mathematical formalism work? That's what it means to make sense. That's what it means to understand quantum mechanics, right? That's what they. So is there some physical mechanism that justifies that formalism? Or perhaps, as you've discovered, a fundamental, compelling fundamental principle that justifies that formalism? That's what we need. And then we can say, those of us who want that understanding can say, it makes sense now, now we understand it. Chris Fuchs wrote, where present-day quantum foundation studies have stagnated in the stream of history, it's not so unlike where the physics of length contraction and time dilation stood before Einstein's paper. Patrick Boylan talks about that situation, and I mean, this is a long ago. We don't even see this. You don't even hear about this. You study physics, right? But this is the situation that they had to deal with then. At the end of the 19th century, physics was in a terrible state of confusion. Maxwellian physicists of the time were ready to abandon the relativity of motion and adopt a preferred frame, the rest frame of the luminiferous ether. That's where they were at. Norton points out that even Einstein played the game. Even Einstein worked on those constructive accounts. He was willing to sacrifice the greatest success of 19th century physics, Maxwell's theory, seeking to replace it with one conforming to an emission theory of light as the Galilean kinematics demanded. So Einstein himself was playing that game before he gave up. Why? Well, he writes of this after and says, by and by I despaired of the possibility of discovering the true laws by means of constructive efforts based on known facts. The longer and the more despairingly I tried, the more I came to the conviction that only the discovery of a universal formal principle could lead us to assured results. In other words, he pivoted to what we would call a principle explanation. Remember I talked about you can have physical mechanisms to justify your formalism, or you may have some compelling fundamental principle to justify it. Well, he said, I'm going to go with the latter. I tried constructive accounts. Everyone's trying constructive accounts. The vortex theory, the froth theory, the jelly model, right? and none of it's working. So what is that? Well, you have some compelling fundamental principle that you use to justify some empirically discovered fact, which dictates your kinematics, constraining your dynamics. So what do we have there? Relativity principle, no preferred reference frame. Everybody measures the same speed of light. Then that gives you your time dilation, length contraction, your Lorentz transformations, and then you have to have your Lorentz invariant dynamics. Okay? And today, have we come up with a constructive counterpart to that principal theory? Well, there are actually, apparently, people out there still publish ether theories. So I have said this, and people have said, no, there is one. You should read so-and-so's paper. But to a first approximation, no. There's no ether theories out there. There is no constructive. Everybody's quite happy with the empirically discovered light postulate being justified by the relativity principle. There's no mention of, in relativity here, as Paul Mainwood points out, he is a philosopher of physics and apparently a squeezer of fruit. There's no mention in relativity of how clocks slow or why meter sticks shrink. And yet, physicists are totally happy with this. So, quantum information theorists said, look, this has been decades, same situation, trying to come up with a constructive account of entanglement, mystery of quantum mechanics, and nobody's happy with what anybody else comes up with. So maybe we should take a cue from Einstein. Maybe we can find some compelling information-theoretic principles to justify the structure that we have that makes quantum quantum. And what he did was he put quantum mechanics in the form of a probability theory, just like the form he had for classical probability theory in terms of probability vectors. And he said, look at this. This is pretty interesting. I have these 5 axioms for both of these probability theories, and only changing one word in one of the axioms takes you from classical to the quantum one. The 5th axiom, the reversible transformations between pure states. If you add continuous, you go from classical to quantum. So we're on to something here, right? We see something there. That's very interesting. That was 2001. The community seems to acknowledge that this is the first axiomatic reconstruction based on information-theoretic principles. There was definitely work well before this. Seilinger, Bruckner, I think you have papers published well before this on the idea that information is fundamental to understanding quantum mechanics, and it should be understood in that fashion. But the actual reconstructions, Hardy is generally accredited with this is the breakthrough, the first one that we... And since then, these are just the ones that we cited in our last paper. There are many of these reconstructions. Okay. And quantum information theorists are, today, they're actually pretty excited about what they've discovered. They feel like, yes, we're getting it. If not, totally got it, right? And here's a statement that I got offline from the Mueller group. Can quantum theory be derived from simple principles in a similar way as the Lorentz transformations can be derived from the relativity principle and the constancy of the speed of light? The exciting answer is yes. And we've made substantial, progress on that goal. And I got this, and I thought, Marcus, I got this from your site, but I have since gone back and looked for it, and I can't find it. Whoever owns this, would you tell me where I can... Now, I can't put this in my papers because I haven't verified that I got where I got it. But this is amazing right here. This is why they're excited, right? You don't assume wave functions. You don't assume complex numbers. You don't assume operators. And what do you get out? Unitary transformations, uncertainty relations, the Schrodinger equation, tierless and bound, everything. So, yeah, what are these principles? Because this is pretty cool, right? Well, this is Van Kamp. Like me, he's in foundations, but not in quantum information theory. So what is their reaction to this? Well, since we don't understand quantum information theory, to us, it just looks like you've just taken the mathematics of quantum mechanics and just reorganized it in some sense. Where's the equivalent of the relativity principle in the light postulate there, right? And here's from a paper, 2009, Dekik and Bruckner. And they admit in this paper at that time, Yeah, we do have these principles, but they're based on abstract mathematical assumptions that seem like we need a little more physical motivation for those. That would be nice, right? And in that paper, they got down to these 3. Now, I read Hardy's paper and his 5, and there was a lot of language I did not understand. But when I read these 3, at least for me, I'm not in quantum information theory, but at least these make sense. I can understand these. So I said, this is a tremendous progress. And Hardy even talks about later. He admits, yes, this is great progress over what he had. And this was sharpened down here by, again, Massanis and Mueller. Sorry. But the point is, now you see they're honing it. They're getting it to where it's going to be understandable for people that aren't in quantum information theory, right? And here you see again that key word, continuous. Everything hinges on that, as we're going to see. So, Korinsky, and I hope I found the right pictures for these, because I don't know these people. I looked these pictures up. Did I have him, Adam? Is that him?
That's Adam, yeah.
Thank God. Van Kamp's picture actually got off a real estate website. That apparently is where he's working now. So, all right. So this is a quote from this paper. This is 2018, right? 9 years later, saying, this continuous reversibility, this is the key. And let me read this because this is just absolutely so spot on. We suggest that continuous reversibility may be the postulate which comes closest to being a candidate for a glimpse on the genuinely physical kernel of quantum reality. Even though Fuchs may want to set a higher threshold for a glimpse of quantum reality, this postulate is quite surprising from the point of view of classical physics. When we have a discrete system that can be in a finite number of perfectly distinguishable alternatives, then one would classically expect that the reversible evolution must be discrete too. For example, a single bit can only ever be flipped, which is a discrete indivisible operation. Not so in quantum theory. The state null of a qubit can be continuously, reversibly moved over to the state 1. For people without a knowledge of quantum theory, but of classical information theory, this may appear as surprising or paradoxical as Einstein's light postulate sounds to people without knowledge of relativity. And so the version of this that I want to focus on is from Bruckner and Zeilinger, Information Invariance and Continuity. And I've chosen this version. If they had it in terms of uncertainty, right, Bruckner, but you had this version next to it, like in parentheses, so I stole that one. So. The total information of one bit is invariant under a continuous change between different complete sets of mutually complementary measurements. And this is where the whole thing now allows us to bring it, to make it more tangible to the people outside quantum information theory. This is the key, the continuous, the invariance, and this complementary measurements, because that allows us to establish a reference frame. And you're already seeing, right, invariance between reference frames, light postulate, invariance of C between reference frames. This is it. This is why quantum information theorists say, now we understand it, because you build everything on the qubit, and the qubit, you can see that this is true and what that means, and why that makes everything mysterious in quantum mechanics, the entanglement, right? But let me show you. In other words, I'm going to have to dumb it down for those of us outside of quantum information theory, and I have to show you how that principle, information invariance and continuity, entails the relativity principle dictating the invariant measurement of Planck's constant, giving rise to your qubit Hilbert space kinematics. Now that I can relate to outside of quantum information theory. This is the message I want to take to the Foundation's community about the meaning of your work, okay? Assuming I haven't butchered it. So, where do we get this? Again, stealing from Herr Bruckner's pictures and his papers. So, I'm going to look at a specific instantiation. I'm going to talk about spin 1/2 measurements, okay? Specifically here to make this clear, make it more tangible for those of us that need that. If we create a preparation state up along the z-hat axis, and we measurement at b hat some angle theta with respect to the z hat direction. And we put our qubit probability structure embedded in the three-dimensional real space, which we can do, right, for qubit, uniquely so. And we have our spin measurements, j, x, y, and z along the x, y, and z axes. Then what does information invariance and continuity tell us? The SU2 invariance of the qubit eigenvalues between those different spin measurement operators in Hilbert space per information invariance and continuity entails the SO3 invariance of spin measurement outcomes between different inertial reference frames. This is a mouthful, I'm sorry. Associated with complete sets of mutually complementary spin measurements in real space. Just need one more ingredient, and we have it. And that is, as Weinberg points out, when you measure an electron spin via Stern-Gerlach magnets, you are essentially measuring a universal constant of nature, Planck's constant. And you're done. That's it. The principle of information invariance and continuity entails the invariant measurement of Planck's constant H between inertial reference frames related by SO3, a subgroup of the Lorentz and Galilean transformation groups between inertial reference frames. Essentially, what have they done? The quantum information theorists have generalized from the boost invariance of C of Einstein, and now what their principle of information invariance and continuity entails is the SO3 invariance of H. Boost and SO3, well, you need both of them to form a group, right, the Lorentz group. So that's tangible. That you can relate to. And now, hopefully, you can share in the excitement of quantum information theorists, right? But let's follow through. At this point in the textbook presentation of special relativity, you have an argument. The relativity principle dictates the invariant measurement of C, and then you say, what's the consequence of that? Time dilation, length contraction, and some heuristic form of the Lorentz transformations, right, in an introductory textbook presentation. So let me follow through here with that same thing. To appreciate this, why it's so weird and it leads to weirdness, we have to understand the classical constructive model for spin. You have the little dipoles coming in this inhomogeneous magnetic field, and so you get these all deflections if you have all the different orientations. But what do we find? No, it only ever goes in two directions, up or down. And even suppose that just for whatever reason you had just an up or down here, as I rotated those magnets, then that degree of deflection should shrink and shrink and shrink and shrink to nothing. Essentially, you're moving through the ether at the speed of light and you're standing still. You're measuring the speed of light to be 0. Right? That's what your classical constructive account would say. But nope. Nope. Everybody, information invariance and continuity. As you rotate the magnets, same information. Up, down, up, down. Why? Everybody's got to measure the same value for Planck's constant. No preferred reference frame. All right. So go back to that picture. We had our, classically speaking, according to that model, we had our spin S projected along B. And so we have cosine theta is what we would expect classically. But again, can't measure anything else other than plus or minus 1, h bar over 2, right? According to your no preferred reference frame. So we can only recover this cosine theta on average if we're going to get it out, right? Now Marcus asked, well, why is it on average? Why couldn't I get it in some, that's what you said, like the second moment of probability theory, etc. I can't answer that question, but I naively, I would say, obviously, I have a collection of things. What's their average behavior going to give me? So at least I would start with that, right? So I'm going to get it, I want to get it on average, okay? And this is in accord with, again, if I understand this correctly, the closeness requirement Dakik and Bruckner had in their paper. In other words, you have to think what's going on here. When you make a measurement, a Stern-Gerlach measurement of this fundamental quantum system, the magnetic field has to come from those same systems, right? A coherent aggregate of those systems. So the thing you're using to make the measurement is just making a measurement of what is a subset of itself. Now the collection, the aggregate, the coherent aggregate, behaves according to the classical expectations, the average, the Ehrenfest theorem, right? On average. But the individual constituents themselves do not. Why? Because no preferred reference frame. Apparently, everybody has to, the fundamental principles applied to the fundamental constituents mean that their behavior is not going to be that of the aggregate, okay? So, we have this average-only projection. We expect to recover what we have from our aggregates on average from the individual constituents, which means the individual outcomes are going to be averaging to what we'd have expected from an aggregate behavior. That, with our normalization condition, tells us that the probability of +1 and the probability of -1 outcomes at theta are given by this, which we already know, of course, obvious. And so we see that information invariance and continuity entails the relativity principle and Planck postulate, and this average-only projection. Okay? You can keep that in mind, because that's going to be the key to understanding the mystery of entanglement. And again, all this follows your operational qubit Hilbert space structure. Now your postulate is getting you straight away to this expectation value, whence you're getting your probabilities, rather than the converse. Typically, when you teach quantum mechanics, you would give the probabilities and then derive that, right? So it's the other way around, but it's there. Oh, I throw this in as a bonus, because I found this was really interesting. This is from Hun, and I also think Bruckner wrote this as well. But the classical prediction of your cosine theta b hat obtains because we know the outcome, the max is +1 at z hat, and we say, therefore I know when I go down here I'm going to get some fraction of that. In other words, knowing that maximum deflection is +1 at z hat, now I know everything else with certainty. Okay? So the quantum information theorists say the way to think about this is there's no limit to the simultaneous knowledge of information associated with the measurement outcomes if you have a classical situation. And that is precisely to say your measurement operators commute. But if that's true, that means you're only going to get the eigenvalues out, the +1, -1 eigenvalues out, at that original direction, right? That's definitely going to be a preferred frame. But according to information invariance and continuity, no. That's not true. You've got to adhere to that no preferred reference frame so that at the b hat, you also still have to get +1s and -1s. And so while you know what it's going to average to, you don't know on any given trial what it's going to produce. You can't know. It's impossible. So that means this entails a probabilistic theory of qubits. And, oh, it's Hun. Oh, it didn't pop up there. There he comes. They don't commute. This is interesting because this is saying there's a limit to the amount of simultaneous information that you can possess about a quantum system, and that limit is established by Planck's constant. So the non-commutative algebra of quantum mechanics is also accounted for by the information invariance and continuity. All right. Let's summarize what we have here. We use our relativity principle to justify our empirically discovered fact spin. And we see how that leads to the qubit Hilbert space structure, or the kinematics of quantum mechanics. As Stern and Gerlach rotated their magnets, they saw no change in the deflection pattern of the atoms. Likewise, the relativity principle justifies the empirically discovered fact. Everyone measures the same speed of light. And that leads to your Minkowski space, or the kinematics of special relativity. As Michelson and Morley rotated their interferometer, they saw no change in the interference pattern. Okay? And Jeff Booth has made this analogy as well, not quite all the way down to the relativity principle, but he's just very close. The information-theoretic interpretation is the proposal to take Hilbert space as the kinematic framework for the physics of an indeterministic universe. So in special relativity, you have the geometry of Minkowski space imposing constraints. And in quantum mechanics, you have the non-Boolean projective geometry of Hilbert space to impose your constraints. Now, this is interesting, but now we understand from our principle of invariance and continuity that both of these facts actually can be traced right back down to the same fundamental principle, no preferred reference frame. So there are papers written about the incompatibility of non-relativistic quantum mechanics and special relativity. Now, certainly it's not Lorentz invariant, but still, if you believe that there was some incompatibility between quantum mechanics and special relativity, then We've got the measurements. It's not like we've done them. We get the entangled states. We measure and we get the outcomes as predicted. So that would be like saying, oh, I think there's some incompatibility between Newtonian mechanics and special relativity because Newtonian mechanics says it should be Galilean velocity addition, and I went out and measured Galilean velocity addition. Then I wouldn't say, well, there's an incompatibility. No, I would say special relativity is wrong, right? So no, there is no such incompatibility, obviously. And now we see why there isn't. They're both based on the same fundamental principle. Just different transformation groups, that's all, and different fundamental constants. All right, so now let's go through, again, everything here is just a particular instantiation, spin 1/2, entangled particles. We'll be talking about the Bell states. And since that gives us arterialism bound. And again, as usual, we'll have Alice and Bob making their measurements on this state, A hat and B hat. Making their angles alpha and beta, say, with respect to z and relative between each other, theta. And what does the formalism, the mathematical formalism, quantum mechanics tell us? Here's the correlation functions for each of the spin states for their measurements. Here are the SU2 symmetries that are obeyed by the states themselves. The singlet state obeys all 3 functional forms, and each of the triplet states is only symmetrical, right? And it goes as cosine theta in a particular plane. Okay. So, this is your time dilation. This is what we want to account for, right? This is our time dilation link contraction business. How does our principle explain this behavior? Well, let's look at the triplet state in a symmetry plane. Suppose you're making the measurements, and it's saying when they're the same. Theta is 0, then you got to get the same outcomes, right? Half the time up and half the time down, but they're the same. And so you're thinking, well, how can we account for that fact? This is the same argument that Bell made, right, in his paper. He said, well, wait a minute. If we know this one, and we know what that one's got to be, and this could be anything over here, and this could be anything, unless there's some kind of superluminal communication going on, because these could be space-like related measurements, how do the particles guaranteed to always get the right outcomes, theta 0 outcomes, the agreement, right? So let's assume Alice is going to make one of 2 measurements and Bob's going to make one of 2 measurements. And they don't have to be the same for this particular situation, but the particles don't know that, right? They've got to be ready in case they are the same with instruction sets. They have to be ready to, if we're measured at this angle, right? Let's go, both agree this time will be plus. Okay, let's go, boom, but that's got to be set for every possible measurement. So let's assume, and I'm following the formalism here from Perez, Merman, many others for the CHSH inequality, right? So there's going to be these 4 measurements. Alice is going to do A and D, Bob's going to do B and C. And they can all they got to be ready, set for each trial in all 4 possibilities. So they'll marry up if they're right, if they're measured the same way. And they can be each plus or minus 1 for each of these, and that tells you this gamma mathematical entity can be plus or minus 2. And so if you were to average this over many trials, then you're going to have to get something between minus 2 and 2. Obviously, that's your Clauser-Horn-Simony-Holt inequality. Experimentally, of course, you can't measure the entire instruction set because you do your measurement and boom, that's it. You've changed everything. States change. So you're really doing these collections of measurements at the different orientations, each one of which is accounted for quantum mechanically by the relevant expectation value, which we said, again, in the symmetry plane for a triplet state. It's just cosine of the angle between those 2 things. And now you let Alice orientations be at 90 like this. Bob's be rotated 90 relative to each other and rotated by 45. And you get your gamma experimental to be 2 root 2 outside the bounds, right? So that's the mystery. We need to account for this. Now, trying to account for this via constructive methods, constructive efforts, like ether theories, right, equivalent, people have been doing that for decades, and a lot of people think they have it. I have it, but the problem is I need superluminal causal pilot waves. And other people go, I'm not going for that. No way, I don't like your idea. I'm going to have the future causing things in the past, retrocausality. It's 2 states vector formalism, transactional interpretation from Kramer, right? And other people are, oh, come on, that's ridiculous, the future causing the past. You can't have causal flowing, And now it's gotten so ridiculous, you probably have heard, superdeterminism is on the table. I'll show you that in a minute, how crazy that is. But those are all constructive accounts. No one's buying anybody else's. Okay. So what we need to do, like Einstein did, step in and end this confusion. Forget the constructive accounts. Let's do the principal account. Okay? Let's show why this has to happen according to this compelling fundamental principle. No preferred reference frame. I think that's fairly compelling. At least people are sold on it in special relativity. Why not quantum mechanics, right? All right, so we'll look at the triplet states in the symmetry plane. And we have, Alice at alpha and Bob at beta, for example, and you'd write out the data. Looks like this, maybe for n trials. And again, no preferred reference frame would tell us she's rotating her magnets 50-50 up, down, all directions. Bob's rotating his magnets 50-50 up, down, all directions. And so if we partition this data according to Alice's equivalence relations, her +1 and -1 results, right? Then this is, with this assumption here, no preferred reference frame for each, then we see what we need to explain to understand the correlation functions, which give rise to that 2√2 tierless and bound amount, right? We need to understand, why does Bob average what he does when Alice measures +1, and why does Bob average what he does when Alice measures -1? Well, again, just like we had when we said we know the state coming in here is the z hat spin up direction, and Bob should be, b hat should be cosine. The exact same thing here. Alice is saying, look, Bob, if you had measured the same way as I did, you would have got +1 when I got +1 and -1 when I got -1. And therefore, when you measure off at this angle theta, b, you should be getting this plus or minus cosine theta. It's as simple as that, Bob. You're not measuring that. I don't know why. Your measurements are crap. But if you average them, they seem to work out, all right? That's because Bob can't measure anything. He has to also measure the same value for Planck's constant, but it averages that. Well, if it's going to average that, bingo, stick that back in there. It falls right out. There you go, cosine theta. And then if you want to get the joint probabilities, this is average-only conservation. Because remember, the reason we have these entangled states is because your spin angular momentum is conserved, right? So it's only conserved here on average, trial-by-trial basis. All right, so let's put this down here and here. That's your average-only conservation. Then what we started with, the 50-50 outcomes in all the directions. And then that gives you your joint probabilities for your quantum mechanics, right? Now, everything there was Alice belittling Bob because of his horrible outcomes. But of course, Bob could have partitioned that data according to his equivalence relations, his +1 and -1 outcomes. And he would have been saying the exact same thing to Alice. Alice, no, my measurement outcomes are great. It's yours that are garbage, right? Keep that in mind. Come back to that. So, Marcus told you we had a book, came out in 2018, Beyond the Dynamical Universe. Jeff Boob is a good friend of ours. He was at the time working at University of Maryland, just an hour south of us from Pennsylvania. So our book came out, and he said, oh, come down and give a seminar, on your book. So, oh, yeah, sure, we came down. And we spent all afternoon and all evening talking about, quantum foundations and things like that. And at the very end of the day, I'm getting ready to leave, and we're going to our car, and he says, here's what I want to know. I want to know why the tier is unbound. For me, this is Jeff Boob talking. For me, that's what it means. Why the quantum? Means why that 2√2? Well, you just saw why. Conservation. Average-only conservation. The only way you're going to be able to conserve it is just on average, because the fundamental constituents have to obey the fundamental principle, the relativity principle. And again, more generally, information invariance and continuity, right? Now, that tells that why this is ruled out. But what Jeff said, there are these other correlations, the Popescu-Rohrlich correlations, and they actually give it all the way up to 4. He called it superquantum correlations. Why don't we see these? Well, of course, if we know why these have to obtain, then we know that's got to rule these out, right? But let's run through that and see it explicitly. So here's your Here are your joint probabilities, which don't, they're no signaling, joint probability. In other words, Alice can't tell what Bob's got from any of her outcomes and her orientations. And Bob can't say what Alice is getting, based on his outcomes. Okay. And I'm going to follow what was in. Have you seen this book by Tanya and Jeff Boop? I actually have my students in quantum. We actually do what I'm going to show you here for fun. Now, keep in mind, I only teach undergraduates, so obviously you wouldn't do this kind of stuff at your level, but for undergraduates, it's fun. So here's what they point out in their book. Suppose we have these coins, he calls them goins, and they behave according to this table. Of course, this is just the PR box, right? So these coins are entangled. So if you start them in heads and flip them, they'll never come out the same. Half the time will be, heads, tails, half the time tails, heads. But never heads, heads, or tails, tails. In every other starting position, they always come out the same. Half the time heads, heads, and half the time tails, tails. And he said, try to come up with some sort of a causal mechanism to explain that behavior. None of these work. These are the only possible ways you can explain it, and none of them work. That sounds familiar, right? We have this violation of the Bell inequality. We try all our explanations, none of them work. The difference, of course, is we've made those. We've created Bell inequality violation states, the Bell states in the lab. We haven't ever made anything like this. The question is, why? Or maybe someday we could? All right? Well, let's follow through. So, whoa, I jumped a little bit faster than I wanted. Sorry. He puts it in the form of a game. Not casino, Quasino. They're at the Quasino, and they're going to play this gambling game. And here's what happens. The dealer places in each of these 5 tracks a 1 or a 0 on each side. This keeps the Alice and Bob here on either side from seeing each other's, what's on the other side there. And all you have to do, the guesser is over here, and let this be Alice, and all she has to do is guess how many lanes have even or odd, not even a number of lanes, I'm sorry, an even or an odd number of lanes that have ones, both have ones. That's it. Okay? So you see here, so you'd have, there's 1, no, 2. So the answer would be even. So the answer is either even or odd. 0 would be conceivably an answer too. So there are 6 options. So it's 50-50. She could pick and win half the time and lose half the time, okay? Now, but there's an additional condition on this, and that is, you see this little piece over here that Bob has, where you can slip in some, you can pass information, but it's going to cost you 1 coin. You pay 6 coins to play, and if you want to pass 1 piece of information, Bob to Alice, you got to take one of those coins off and just give it to the dealer. And that means if you win, instead of 6 coins from the dealer, you only get 5. Right? If you send 2 pieces of information, now you only have 4, you're going to win 4, right? Which means you only netted 2, etc. Okay. So here we have our 2 players, and he goes through this example, and you can see, I don't know if you can make that out here. Maybe go up the next, see if it's in here. Ah, here we go. This makes it more clear. So now on this side, here's your guesser, and you see he's got the 3 ones here. So he just needs to know from his partner, his wife on the other side, he just needs to know, in these 3 lanes, does she have a 1 or a 0? Right? That's what he needs. He needs those 3 pieces of information. So she slips him the information. 1. In lane 1, I have a 1. Here's hers. In lane 2, I have a 0. In lane 3, I have a 1. And he says, that's all I need. Stop right there. We're good to go. Now I know the answer. It's here. It's odd. It's just the 1 lane where we have the match. Okay? So he says, did you have 2? Oh, 2 matches. Didn't he have 2 matches? 2 matches, even. 2 matches. Bing, they win. But now they spent 3 coins to get that information over, so they win 3 back from the house, but 3 and 3 is 6, right where they started. Ah. And they walk away saying, well, at least we didn't lose anything. And then this one says, boy, I challenge anybody to beat this game on average, right? Well, the quantum information theorist said, if you could make these goings according to the PR box, you can beat this game every time with one piece of information every time, guaranteed. Now, the quantum information theorists said right away, well, that doesn't just seem like good. That seems unreasonably good. I mean, that seems ridiculous, right? Well, they're not ridiculous about how it's done. What I'll show you here, they understood immediately. But the fact that you could do this somehow, that just seems unnatural. If we could really communicate with this degree of effectiveness, that just seems unrealistic. So here's what they quickly realized. If you could make these, so now here's what happened. Alice and Bob are going to bring 5 sets of these entangled goings with them. And here's what they're going to do. Each one, without seeing what the other side, it doesn't matter what's on the other side. So Alice has a 1 in her lane. She'll start her coin with the heads and flip it. She has a 0. She'll start her coin with the tails and flip it. That's the rule. That's all she has to do, flip them. And then she looks at her heads and tails, and she says, do I have an odd number or an even number of heads? Bob does the same thing. He flips his. Does he have an odd number or an even number of heads? Well, all Alice needs to know right now is, does Bob have an odd number of heads or an even number? That's all she needs to know. Guaranteed to win. Because with the coins, if Bob has the same as she has, he has an odd number and she has an odd number, or he has an even number and she has an even number, that means they must have an even number of lanes with 1s. Otherwise, it's an odd. Done. Guaranteed to win 4 coins every time. So, can we do anywhere near that well with quantum, our maximally entangled qubits for say the triplet state? Well, let's make a physical instantiation of this here, right? Cosine squared theta for like outcomes, sine squared theta over 2, for different outcomes. And look over what we have over here. What are these things telling us over here, our PR box? So A and B are the same. So that's telling us your A hat and B hat are the same. Over here, A and B prime are the same. So that means A hat and B hat prime are the same. This one's A hat prime and B prime are the same. So those 3 together tell you that A hat prime and B hat prime have to be the same. But no. That's always different. It's exactly the opposite of what we would expect to get with a Bell state. And what accounts for the Bell state? Conservation. So this PR box is violating our conservation principle in a maximal fashion. So it's not maybe that surprising that we'll never probably instantiate these kind of correlations. And so this was our answer then to Jeff Boob. You asked the question, here's our answer. It's a constraint. This is the only one that satisfies the constraint. Conservation in accord with no preferred reference frame, as entailed by information invariance and continuity. So what do we have? Information invariance and continuity entails the relativity principle and Planck postulate and this average-only projection. The average-only projection gives us an average-only conservation, or that is conservation in accord with the relativity principle. So the mystery of entanglement is that average-only conservation, right? And that results from the no preferred reference frame. Again, more generally, information invariance and continuity. The reason we have the mystery is because we're seeking a dynamical explanation, a constructive account for our Bell inequality, right? But remember, what is it in a principal explanation that allows us to get away with this? To have an account, but not have to deal with all these problems of those constructive efforts? Well, we have our compelling fundamental principle being used to justify an empirically discovered fact, which dictates our kinematics, and thereby constraining the dynamics, okay? Now let's revisit the Bell inequality and look at the assumptions the people who are trying to come up with a constructive account have to face. All right? I got these off of SEP, Stanford Encyclopedia of Philosophy. There's many different ways to articulate the assumptions that go into them. So the first one, you're assuming that there's something going on. There's something physical responsible, some physical mechanism, and you characterize that by what you call your hidden variable, your lambda. And then you're going to assume statistical independence, that there's no correlations between this lambda and the detector settings. And then you're going to assume local causality. And that is the correlations must be explained in causal fashion along future-oriented time-like relations. Okay? Those are all the assumptions. Now, that means for the people who are trying to beat it and explain what's going on, right, constructive methods, they're going to have to sacrifice something. So here, the de Broglie-Bohm pilot wave, that's going to get rid of the time-like here, right? It could be space-like causal relations for them. Retrocausality, future-oriented. Now, this says, no, we'll drop that. You can actually have the information. But we really would need to know, what are those settings that I'm going to encounter for sure when I leave the source? If I know that information at the start, then I have a causal relation going backward in time to the source to make sure that everything works out as necessary, right? And now you also have superdeterminism. And this one saying statistical independence. We're going to allow that to be violated. And Sabine Hosenfelder, Gerhard Tuft also are people that are advocating for that right now. But you can see the analogy with special relativity's development, right? The degree of desperation. They're going all the way to superdeterminism now. Let me show you just so that you can appreciate how desperate the situation has become for the people who are trying to account for this in constructive fashion. Remember those four terms in the gamma experimental? And I noted that they are, in fact, individual terms, experimentally speaking. They all stand for their own experimental situations. Mathematically speaking, then, any of them could be plus or minus 1, which means, purely and mathematically speaking, it's possible that gamma experimental could be as large as plus 4 or as small as minus 4. But how would that have to happen? Well, here are all the instruction sets, the 16 instruction sets that are possible for the experiment. If you want to get gamma experimental to be plus 4, and you want Alice and Bob at the end of the day to say, hey, I created the same state every time, and we did the 4 measurement configurations with equal frequency, no bias at all, then you're going to need to do something like this. It's going to have to be the case, for example, when this instruction set is created, that Alice and Bob never choose to measure it in DC. They choose AB, AC, and DB with equal frequency, but they never choose this one. And when this instruction set is created, they never choose AC. You see that? Now, if you add these up, they all add up to be the same number overall. So again, Alice and Bob think they're in accord with statistical independence. Their 4 options are being exercised uniformly, and as far as they know, it's the same state every time. But what's going on in the background is this. How are you going to ever account for something like this? And Sabine admits it's going to be horrible, especially if you're talking about humans making choices. Now you're going to have to go all the way down to trying to explain causal mechanisms in human brains. And whatever you use to explain that, keep in mind, is also going to have to apply to monkeys throwing darts or the Swiss lottery system. Anything you can imagine that's making these choices, your mechanism that's making this happen in the background has to apply to that situation. Yeah. Good luck. No. Forget it. We got our principal account. Look at the average view for the spin triplet states. So suppose this is Alice and her +1 outcome trials for each of the thetas, and there's what Bob's averaging. And that makes perfect sense in the aggregate, on the average. But again, note, so for example, if at 90 degrees, Bob's averaging 0. What would Alice have to say about that? Bob, you're averaging 0, yes. But +1 and -1, those are as far away from 0 as you can get, Bob. And every experiment you run, you're getting the worst possible outcomes. You're not getting a Gaussian averaging to what you expect. No, you're getting bimodal and the worst possible wrong answers. Averaging, this is ridiculous. Bob, your data are crap. But wait, Bob says, no. Let's partition the data according to my equivalence relations. Then we see, Alice, it's your data that's garbage. You're the one that's violating conservation as horribly, as egregiously as possible. Now, I don't know what I'm finding when I talk to the quantum foundations people. that they don't have, because the last time they took special relativity, maybe as an undergraduate, in graduate school certainly had nothing to do with relativity of simultaneity, time dilation. In graduate school, special relativity is all about Lorentz transformations, the boost matrix, and all that stuff, right? But I'm going to take you back to your undergrad days, however many years ago that is for you, and point out here that this is exactly the same thing that happens in special relativity. Where Alice says, Bob, she partitions space-time according to her equivalence relation, her surfaces of simultaneity, and she says, Bob, your meter sticks are short and your clocks are running slow. But when Bob partitions space-time according to his equivalence relation, his surfaces of simultaneity, he can look at Alice and say, no, 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 Alice, your meter sticks are short and your clocks run slow. Again, we're following exactly the presentation of special relativity at this level, where Einstein says boost invariance of C, and everything that I'm showing you is SO3 invariance of H. So let's run through quickly what I show my students. These numbers, days, and the time differences you see are actually greatly changed from the actual numbers that you would get from your Lorentz transformations to make the point more tangible for my undergraduate students. So for example, this 2.5 is like 2.5 microseconds. These are kilometers. The relative speed is 0.6 c, etc. So here's what we have. Those 4 events, don't worry about remembering these 4 events. You'll see them in the diagram. But Joe and Bob and the girls, Alice, Kim, and Sarah, all agree on these facts right here. They all agree. So Joe and Bob say, look, we're the same age. So event 1 and event 2 happened when we were 20 days old. We were the same age. These are simultaneous. And look, the girls claim that Kim and Sarah are 1,250 meters apart. But look, no, they're only 1,000 meters apart. That's because their meter sticks are too short. More of them fit in that interval. But the girls say, whoa, wait a minute, wait a minute. We're the same age. We're all 20 days old when this event happening. So here's the event that happened at the same time as event 1 with Alice, right, meeting Bob. And the distance between Sarah and Alice is 800 meters, not the 1,000 that the boys say. The boys' meter sticks are short, not ours. And look, we aged 2.5 days between event 2 and event 3. Bob only aged 2 days. Their clocks are running slow. Now we got to bring it full circle. Sarah and Bob meet, and Bob has aged 5.6 days since Joe and Sarah met, and Sarah's only aged 4.5 days. So clearly, it's the girls' clocks that are running slow. So again, that was just to remind you, days gone past for you, I'm sure, that you don't remember how that worked. But now do you see how it's more than just an analogy? It's exactly the same. Those weirdnesses, time dilation, length contraction, relativity of simultaneity, entanglement, non-commutative algebra, those mysteries all happen for exactly the same reason. Fundamentally, no preferred reference frame. So to bring it to a conclusion, 2 more slides. Here's a quote from Bell. He gave a talk, and this was transcribed from the questions after his talk. Someone asked him, when do you think we're going to have this resolved, John? And he said, I think the problems and puzzles we are dealing with here will be cleared up. And our descendants will look back on us with the same kind of superiority as we now are tempted to feel when we look back at people in the late 19th century who worried about the ether. And Michelson Morley, the puzzle seemed insoluble to them. And came Einstein in 1905, and now every school kid learns it and feels superior to those old guys. Don't we? I mean, don't we think it's ridiculous, ether theories? Don't you imagine yourself being back there and saying, well, I surely wouldn't have been playing with no ether theories. That's just ridiculous, right? I mean, we kind of, maybe you don't. Maybe you're saying, Stuckey, you're so conceited. But I don't know. That's what he's pointing out. Now it's my feeling that all this action at a distance and no action at a distance business will go the same way. Someone will come up with an answer, with a reasonable way of looking at these things. And if we're lucky, it will be some big new development like the theory of relativity. Prescient, wasn't he? The axiomatic reconstructions of quantum mechanics based on information-theoretic principles reveal the relativity principle at the foundation of quantum mechanics precisely as it exists at the foundations of special relativity, demanding the invariant measurement of a fundamental constant of nature. Oops, I clicked the wrong button. I wanted to press my laser pointer. Oops. There we go. Thus, this is the conclusion. Thanks to the quantum information theorists, we now understand quantum mechanics as well as we understand special relativity. And yes, I mean thanks to you. Thank you. All right. And now my mistake. Oh, Bruckner. Okay. Brooke, I'm sorry. All right. How many mistakes did I make?
So, thank you for your talk. I certainly sympathize with the whole program of this principal explanation. I would have two questions. One is more technical, one is more conceptual. The conceptual one is, it seems that the role that light velocity played in theory of relativity, h bar here, are quite different, and it doesn't seem necessary to involve it at all at the level I think we discussed during this talk. Because this was just a unit for the spins, and one can multiply this and
absolutely.
Distribution.
Absolutely true.
So
yes.
I wonder if you have some insight how h bar would be entering the game more significant. And the second question is that, this is more technical. I understand that it works well, accepting all the principles, as long as we have binary outcomes.
Yeah.
Because then the average value already defines the probability for each of the two outcomes they have to.
Right.
So knowing the average value, we know also the probability. And then we can say, well, let's assume the average value like in classical physics, and then derive the probabilities for the quantum case. But now, as soon as we have more than two outcomes, this will not be sufficient because we will not have enough parameters to decide what the probabilities will be.
Let me respond to the second question first, because that's where I'm least qualified. That's the, apparently, from what I understand, you've reconstructed the whole of your denumerable dimensional Hilbert space, which you can say a higher number of outcomes space, from the qubit structure alone. So all we're explaining here is that fundamental qubit structure. And then everything follows according to your reconstructions, if I understood that correctly. Okay, so then whatever else you do from there to get those higher dimensional states, you would follow from this behavior with the qubits. That would be my response there. I don't know if that, okay. Conceptually, again, the h bar, yes. This is my co-author. I'm going to out him here, Michael Silverstein. He has said, it seems to him naively, that information invariance and continuity isn't necessarily more fundamental than the relativity. Shouldn't the relativity principle be like more fundamental? And I said, well, the problem is, like you said, in this particular instantiation, we're measuring h, so we want to make that Planck postulate based on what we actually measure. But what the quantum information theorists did is they looked at the qubit structure in general. It doesn't matter what the two outcomes are. Let's call them +1, 0, +1, -1, 5 and 3, whatever. It makes no difference. Whatever that corresponds to, when you instantiate it physically with your closest requirement, is going to tell you that you have to get the 5 and the 4, the 3 and the whatever they are, minus whatever. And your classical expectation for that, for your aggregate behavior, is going to be something that you have to average those to get, because that's what you're going to build the classical things that you're using to measure your quantum things with. So where does the h come in there? Well, borrowing from what Hun said, still it's a fact that simultaneous measurements and information is available to you only with that limit. Did I misunderstand that? That h bar establishes a minimum, a limit that you can go for regardless of what that information is about. Even if you're not measuring directly h. H is still establishing that minimum value of simultaneous knowledge that necessarily has to be true, because you always have to get the two outcomes and only average to get the results in between. I'm asking you now.
I would say,
do I understand the?
I don't see necessity as long as when we speak about spin, but if we speak about something like
Yeah, XP is IH bar there, yeah.
But I was wondering if one can arrive at H bar without going into this more obvious way of going into the phase space. But I don't have an answer. I'm just
Okay. Well,
Thanks.
neither do I. Wow. Well,
Okay, so maybe
thank you
we
very
can
much for your
postpone
attention.
all further questions to discussions. Whoever wants to, he's here for a few more hours. So let's thank the speaker again.
Thank you, thank you. Oh, that's fine. Thank you. I've spoken with Marcus about your approaches to quantum gravity. That's what I'm really interested in. I think you guys got it spot on, and he can tell you why I think that. But I think you guys are this close to quantum gravity. He doesn't see it that, but I do. Okay.
Thanks.
All right. Hi. I'm sorry. I've lost a lot of my hearing, and so I'm going to have to get kind of.
What kind of structure, theoretical structure, do you get to if you assume the two invariability, the one in your invariability and the one in special relativity at the same time?
I'm sorry, what kind of mathematical structure do you get for, oh, are you trying to include the Hilbert space structure with the Minkowski space structure? You're saying that those are...
I was wondering, because now if you're right, they are right.
Yeah, it's them, not me.
So if they're right,